What's your name? Okay. Alrighty, so let's go ahead and get started today. So these are the topics we're going to go over during the lecture part. The lecture is probably going to be longer than an hour. It'll be like an hour, 15 minutes or so. We'll see how it goes. We'll probably take a break at some point. But then there's an activity on what the lecture is about. And then after that, you'll have time to work on Lab 0. So after the lecture and activity, you'll have enough information where you can finish Lab 0. Okay, and that's due Monday at midnight. Okay, if you have time tomorrow or the weekend, also Monday if you need it to finish that lab. Over on the sideboard, as you can see, I have there's going to be 14 groups, 14 two-person groups. So just at some point before we start the lab portion, if you know who your partner is going to be, write both class names under whatever group number you want to be, and those people have done. There's already how many groups? Actually, 5 groups it looks like. If you don't put your name up there, with, with the partner, I'll just assign groups. Okay, I'll do that like I said before or after the activity. Actually, while you're working on the activity, I'll probably do that. So at that point, or before that, you would want to write your names up there if you know who you want to work with. Okay. All right. So, the other thing, I don't know if I mentioned this last class, but in this case I didn't. This is the code to this door. So if you have to get into this room to use the computers or the basis board, and as long as you can get into the building, you'll be able to get into this room if you have that code. So you might want to take a picture of it or write it down somewhere. All right, so where I want to start today is just talking a little bit about, these bits 0 and 1 that we have in base 2. We talked about the different number bases, concentrating on the ones that are particularly important for digital, and binary base 2 is an important base for anything that you're doing in digital. Well, these bits 0 and 1, they're shorthand for voltages in a circuit. Okay, now, again, I realize not everyone has taken circuits and you're not going to be tested on circuits, but I just want to give you some idea that in a digital circuit, it's not like you have 0s and 1s that are kind of, in that circuit. What we do have our voltage. Okay, voltage is a force that actually gets charges to move that we call current. And those are the two main quantities, or two of the main quantities in an electrical circuit that we have. Those of you that had some circuits know about voltage and current, I'm sure. So let's see, 0 volt or 0 typically corresponds to 0 volts. And 1 corresponds to some plus amount of voltage. Usually it's plus 5 volts. Sometimes it's 3.3 volts. Again, you're not going to be tested on any of this, but I just want to make sure that you have the understanding that, these 0s and 1s are not like actual numbers that are in the digital circuit. Those numbers represent voltages. Okay, they're voltages on like a wire or a pin or something like that. Okay, and then also, these are ideal values. Now, I know some of you have had a circuits lab, right? Because the EE majors, you take, what is it, EE151? How many people have taken EE151? Oh, not as many. I thought there was many more EEs. Okay. How many people don't like raising their hand? Why'd you raise your hand? Yeah, gotcha. But in that 151 class, I'm sure you made voltage measurements. Right? People that took 151, did you take like a voltmeter, well, a multimeter, and you choose volts and you connect it up to a circuit, and the display will show a number, and that's how many volts you have in that part of the circuit? Well, those of you that have made a voltage measurement, typically when you make a voltage measurement, are those numbers that are displaying the voltage, are they nice and steady? Or do they typically fluctuate some? Yeah, they typically fluctuate because, when you have a circuit that's powered and currents running through components, those components heat up. And when those components heat up, it changes their resistance, which changes the current through them, which changes the voltage across them. Okay, so that's why you get this typically a fluctuation in voltage. So, ideally we say a 0 is this exact amount of voltage, right? 0 volts, and a 1 is this exact amount of voltage, 5 volts or 3.3 volts. But in reality, in actuality, we're going to say that a 0 is a voltage that's below a certain amount of voltage. Like example, a lot of times it's 1.4 volts. Right? So if I have a voltage somewhere in a circuit, and it's a digital circuit, and that voltage is less than 1.4 volts, well, we call that a 0. And if you have a voltage that's greater than that 1.4 volts, well, we call that a 1. Okay? But like I said, the main reason I'm bringing this up is just that, remember, these 0s and 1s, they're not like 0s and 1s running around in a circuit. They represent voltages. Now, another thing is, 0s and 1s, these voltages in a digital circuit, they can represent anything the designer wants. Okay, we talked about number bases last time, and we talked about base 2 binary that has the characters 0s and 1s. Well, that's just one thing that a designer can design a circuit for. A designer can design a circuit so that the 0s and 1s mean a number. They have numerical value. But the 0s and 1s, they're just voltage levels. They don't inherently have any particular use. The designer decides what the use is. So these 0s and 1s, they can represent color, they can represent sound, they can represent pixels on a video screen. I mean, they can represent anything. Okay, it's the designer who decides what the 0s and 1s represent. They don't always represent numbers. They can, but they don't always. Okay? Right. The other thing that's very important is the number of values that I can represent with a certain number of bits. Okay? If I only have one bit, well, that one bit can either be 0 or 1. Right? So if I just have one bit, and we call a digital signal a bit. Digital. In fact, these are examples of what digital signals look like. They're square waves, right? Because a square wave only has 2 possible values, right? The low value, the high value. Okay. Well, if I have 2 bits, 2 digital signals, with 2 bits, I could either have both bits being 0 at the same time, or I could have this bit equaling a 0 and that bit equaling a 1 at the same time, or this bit could be 1 and that bit could be 0 at the same time, or both bits could be 1 at the same time. So if I have 2 bits, I can represent 4 things. I can represent 4 values. Okay. If I have 3 bits, I could have all 3 equal to 0, or I could have 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 2, 4, 6, 8. I could have 8 different values if I have 3 bits. So do you see a pattern? 1 bit, 2 values. 2 bits, 4 values. 3 bits, 8 values. Can you guess what 4-bit values I would have? 16. 5 bits, 32. 6 bits, 64. See, every time I add a bit, I double the number of values that I can represent with that number of bits. So the important relationship to know, and this is something just to memorize at first, but you're going to see this so often, eventually it just gets ingrained in your head, in that 2 to the number of bits equals the number of values that you can represent with those bits. Right? There's 1 bit, 2 values, 2 bits, 4 values, 3 bits, 8 values, 4 bits, 16 values, and so on. Okay? All right, so any questions up to this point? Everybody's good?
If you're using hexadecimal, would it be 16 to the power of the fifth?
Well, really the hexadecimal use in digital circuits is just sort of a shorthand for any long binary value. So, you know, you could certainly probably come up with something that is like this for base 16, but it wouldn't really be useful. Yeah, the real use of hexadecimal in digital is just that we have a long string of bits. Like, for example, in CPE133, the follow-on class to this one, all the data is 32 bits. So instead of saying, you know, like 32 bits, you can just say 8 hex characters, right? Because it's just shorter.
Okay. Yeah.
Any other questions? All right, next thing is we're going to talk about logic gates. And on each table, should be a handout. Well, there's 2 handouts, but the one that is important for what I'm going to be talking about in the next 15 minutes or so is this one right here that has the, let's see, the title is Basic Boolean. I just put one on the table. At some point, you might want to take a picture of it just so you have your own copy of it. So the first logic gates, this is logic gates. Okay, the first logic gate we're going to talk about is the NOT gate, okay, which is also called the inverter. And it has this logic symbol. It's an arrow with a little bubble. This is the input side. This is the output side. And typically with logic gates, we'll label the inputs and outputs with variables, you know, usually, you know, some letter. So for example, if I label that input A, the output of the inverter would be shown as A with a bar over the top. Okay, and this gets into Boolean algebra. Okay, Boolean is just a person's name. But in the digital world, since we're dealing with base 2, the algebra that's used is base 2 algebra instead of base 10, what you used. So also on this handout, besides the different logic gates, there's tables of laws and theorems for base 2 algebra, Boolean algebra. And we're not going to go over all of these. We're going to pay particular attention to one of them called De Morgan's today. And throughout the quarter, you know, there'll be a few more that we talk about here in class, but I just give you all of them, though we're not necessarily going to use all of them, just so you have them there as reference. And if you take a look, you'll see that some of like the properties, like associative property and things like that, they're the same as what you learned in base 10. But then there are a lot of different rules, you know, that are particular to base 2. De Morgan's is one of those. It's particular base 2 that we'll talk about today. But you see this bar over a variable, that's a base 2 algebra symbol. And what that bar means is not. And what not means here is opposite of. Okay, so we have input A and the output's going to be opposite of A. And since this is a logic gate, and logic gates are used in digital circuits where you only have 2 possible values, either a 0 or a 1, well, the truth table, okay, and a truth table is just a table that shows what the output would be for all possible inputs. And we always put inputs on the left side of the truth table, and we always put outputs on the right side of the truth table. So here, when the input A is 0, the output not A is going to be 1. When the input A is 1, the output not A is going to be 0. Okay, that's why it's called an inverter. You just get the opposite out of what you put in. Okay. So any questions about the inverter, the NOT gate? All right, let's talk about the next gate. The next gate is the AND gate. Okay, and the AND gate has this logic symbol. Now, this is a 2-input AND gate, right? Got inputs A and B. But you can get AND gates that are 3-input, 4-input, 8-input, 16-input. Okay, there can be more than just 2 inputs to an AND gate. Now, some more Boolean algebra. The way that you write when you have inputs that are ANDed together, so this gate is going to AND A and B together, is you can write it just like this. Sometimes a dot is used. Okay, but see, when you're ANDing in base 2, you can write what you're ANDing together just side by side like this, just like in base 10 when you're multiplying. And if you take a look at the handout, at the top of the truth table for the AND gate, it has logical multiplication. Okay, the reason they say logical multiplication is because if you were to look at this as a base 10 equation, it would look like you're multiplying. But that's not what's happening here. Okay, what's happening here is these 2 inputs are being ANDed together. Okay, they're not being multiplied. Okay, again, it's only called logical multiplication because of the way it looks. Okay. What an AND function is described by looking at its truth table. Okay, so since I have 2 inputs, right, 2 inputs that can either be 0 or 1, how many combinations can I have? Right, either both 0, 0, 1, 1, 0, 1, 1. Okay, well, an AND gate will only give a 1 output when all the inputs are 1. If all the inputs are not 1, then you're going to get a 0 out of an AND gate. Okay, and that's true no matter how many inputs you have. Right, 2 inputs, both inputs have to be 1 to get a 1 out. If you had an AND gate with 16 inputs, all 16 inputs would have to be a 1 to get a 1 out. If only one of those 16 is a 0, you're going to get a 0 out. Okay. So any questions about the AND gate?
If there's more than 2 inputs, you just make you just add bits to the information.
To this table?
Yeah.
Yeah, exactly. Because let's say I had 3 inputs to my AND gate. How many rows in my truth table am I going to need? 3. I have 3 inputs. How many? 8. Right? Because that goes back to the, we talked about earlier, right? 2 to the number of bits equals the number of values. Right? So if I have 3 bits, there's 8 values. Okay. But the only place, if we have the 8 rows, the only row that's going to have a 1 as the output is the one that has all the inputs equal to 1. All the other combinations would have an output of 0. Okay. Any other questions at this point? All right, let's do the next gate. The next gate is the OR gate. And the OR gate has this symbol. As you can see here, curvy. Or here it's a vertical line. In Boolean algebra, OR is the plus sign. Okay, so this is A or B. But because it looks like you're adding, right? If you were to consider this to be a base 10 equation, that's why on the sheet you'll see that the OR is called a logical addition, logical sum. Okay, but again, addition's not going on here. The OR function is going. And the truth table for an OR gate looks like this. In OR gate, you'll get a 1 out as long as at least one of the inputs is a 1. If see we get a 1 for these combinations, we'd only get a 0 out of the OR gate when all the inputs are 0. So again, this applies no matter how many inputs you have, 2, 4, 8, 16, whatever. Right, you have 16 inputs to an OR gate, as long as at least one input to 1, you're gonna get a 1 out. You get a 0 out of an OR gate, all 16 inputs would have to be 0. Okay? So any questions about the OR gate? All right, now I'm going to go over 2 more logic gates that's not on that handout. Okay. And the first of these 2 that's not on the handout is the NAND. Okay, and NAND stands for not AND. And the symbol for a NAND looks like this. Okay, so before I go any further, compare the NAND gate symbol to the AND gate symbol. Can you tell me what's different? The circle. Yeah, there's a little circle here at the output for the NAND that's not there for the AND. Well, the reason for that is because a NAND is equal to a not AND. So if you take an AND gate and you put an inverter on the output, that's the same as a NAND. So, you know, where this symbol comes from is kind of like, you know, this inverter symbol was squished into the AND symbol and they just left a little bubble sticking out. Right? That's just to remind us that, hey, the NAND's just like an AND, but it's got an inverted output. Okay? And the Boolean equation for a NAND gate, actually, we'll start here. Well, since an AND is equal to an AND, then an inverter, well, first these 2 inputs get ANDed together. So you see you'll have AB here. Then that A and B that have been ANDed together, the whole thing gets inverted. So you see, it look like this. The A and B are ANDed together first, and then the whole thing's inverted. Okay? Now, here's the truth table. For a NAND. So the truth table for the NAND, the output of the NAND is just going to be the opposite of the AND. So an AND gives you a 1 out when all the inputs are 1. A NAND gives you a 0 out when all the inputs are 1. Otherwise, you get a 1 out. Right? We're over here. If all the inputs aren't equal to 1, you get a 0. Right? So you see, it's the same truth table except the output is inverted. Okay. So any question about the NAND? All right, what do you think's coming next? What gate's coming next? NOR, exactly. There's a NOR gate. Stands for not OR. It has this symbol. It looks just like the OR gate symbol, but it's got a little bubble on it, on the output. And it's equal to an OR gate with an inverted output. Okay, so first, the inputs are ORed together, so you get A or B. And then those inputs have been ORed together, the whole thing gets inverted. So Boolean, the Boolean expression looks like that. F equals A or B, the whole thing inverted. Okay, and then the truth table. Well, it's going to look just like the OR, but the output's inverted. So the OR, you get a 1 out as long as at least one input's a 1. With the NOR, you get a 0 out as long as at least one input's equal to 1. The OR, you only get a 0 out when both inputs are 0. The NOR, you only get a 1 out when both inputs are 0. Okay? So these gates, AND, NOR, and the inverter, the NOT gate, these are what are considered like the basic gates of logic. Okay, they're like the building blocks of all circuitry that does digital. You know, everything that does processing in a computer all relates back to these gates. Now, there's two other gates called exclusive OR and exclusive NOR. They're not basic gates. They're actually made up of several of these gates. We'll get to those gates next week. One other thing I want to point out before we continue is the other handout that's on each table shows a 2-input NAND gate. It shows the circuit or a circuit. There's more than one way to make a NAND gate. But the reason I give you this handout, and again, you're not going to be tested on circuits, so you know this is just informational. It's not testable. But you see these symbols that we write here, these logic symbols, they all represent tangible circuits, tangible electronic circuits. Okay, so you know, instead of writing this circuit every time we have a NAND gate, we can just put this symbol. Okay, that symbol represents a circuit like this. Okay, you know, these circuits contain transistors that are being used as switches. So you'll learn about transistors later on in the science class. You know, diodes, that's what these symbols are. They're semiconductor components. You learn about them also later on. You know, resistors is one of the first things you talk about when you take the first circuit. Okay, so eventually you'll understand how this electronic circuit gives you this truth table. Okay? All right, so any question about logic gates? Is that all good? All good? Okay, because I'm going to erase all this if there's no questions. All right, so let's move on now. And let's talk about truth tables and SOP, the Morgans, all the really good stuff today. Not that this wasn't good. Things are just going to get better. All right. So as I mentioned when we were talking about the gates, a truth table will show you all the outputs for every possible input combination you have, whether it's for a gate or some sort of circuit or you know any sort of design. Okay. So I'm going to make this truth table. And on the input side, I'm going to use a variable C, and you'll see what this stands for in a second. G and S, and I'm just going to have one output that I'm going to use E. And since we have 3 inputs, and those inputs are binary, they're either 0 or 1. How many possible combinations do we have? You have 3 inputs, how many combinations? 8, right? 2 to the 3 is 8, right? Okay, right? So they all could be 0, or you can have 0, 0, 1, or 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 2, 4, 6, 8. Now notice, when I wrote these combinations, I put them in binary order. Right? If you were to take these as a binary number, 0, 1, 2, 3, 4, 5, 6, 7. Right? By convention, that's what we always do. Okay, in truth tables, you always put your inputs in binary order.
What are the CGS?
Yeah, that's the next thing. Oh. Yeah. Yeah. What the C stands for here is chips. Like tortilla chips. And the G stands for eggs. And the S stands for salsa. And the E stands for eat. So I'm going to show you the output of this truth table based on my appetite. Okay, so this is just me. Your truth table might be different. Okay. Well, except for the first row, right? Because you don't have any chips, and you don't have any eggs, and you don't have any salsa, you're not going to eat anything, right? So, right, E would be 0, right? Because you know, if it's 0, it means we don't have it. If it's a 1, it means we have it. All right. Well, me personally, if There's just salsa, I don't eat just salsa, okay? Maybe you do, but I don't. Just eggs is fine. Eggs and salsa, that's like my favorite thing. Who else likes salsa on their eggs? Like scrambled eggs? No one else? Oh, okay, there we go. It's like 3 or 4 people, yeah. You've never tried salsa on scrambled eggs, try it, it's like the best. Just tortilla chips by themselves, sure. Chips and salsa, of course. Chips, tortilla chips with eggs, not a fan. And I'm not a fan of including tortilla chips with the eggs and salsa. All right, so you see, based on my appetite, these 4 combinations I would eat. These 4 I wouldn't. Okay, but you see, this shows the purpose of a truth table, right? It shows what your expected outputs are going to be for all possible combinations of inputs. Okay. All right. The next thing is SOP. SOP stands for sum of products. Okay, and this is a form of Boolean equation. EQN is my abbreviation for equation. Again, Boolean is just a person's name, but you know, this is a base 2 equation. Okay, and this is one form. See, there's another form called POS that we're going to get to later, but we're going to start with SOP. And I'm going to write the SOP for when I would eat something. Okay, so output eat. So to write an equation for this output E, which means when I'm going to eat, I look at where E is equal to a 1 in my truth table. Okay, so here in this row, E is equal to 1, and the corresponding inputs is no chips, eggs, no salsa. So I write that as a term. Yeah, I write this input as a term where if I don't have that term, right, if it's a 0, I put a not. And if I do have that variable, right, if it's equal to a 1, I don't put the not over it. So you see, I'll eat if there's no chips, no salsa, but there's eggs. I'll also eat, okay, so we use an or now, right, because that's just one combination I'll eat. But I'll also eat when there's no chips, there's eggs, and there is salsa. Okay, or I'll eat when there's just chips. Or I'll eat when there's chips and salsa. Oops. Didn't mean to put it. This is, I have chips and I have salsa. Right, so you see, this equation that I just wrote that came right from the truth table where the outputs are equal to 1. This is SOP for E. And the reason why it's called SOP, sum of products, is because these terms that are ANDed together and then OR, well, if you consider this would be like a base 10 equation, it would be sum of the products. Okay, but again, multiplication is not happening here and addition is not happening here, right? Because these are getting ANDed together and these are getting ORed together. Right, but they say sum of products because if you were to consider this to be a base 10, like if you were just looking at this as base 10, well, it would look like these are being multiplied and then added together. Okay? So any questions on how I got this? Okay, I can also come up with the SOP for not eat. And now I'm looking at where the output is 0 in the truth table. Right, so one of the terms for not E would be not C, not D, not S, or not C, not G, S, or C, G, not S, or C, G, S. See, this is SOP for not. Okay, summer products or not. Any questions on how I got that? See, it's coming right from the truth table, right? This comes from the ones, this comes from the zeros. Okay? All right, the next thing is De Morgan's. And the reason why De Morgan's is the next thing, and that's one of these laws that's on that handout, is because in order to get this other form of Boolean equation, the POS, which stands for product of sums, well, we have to use De Morgan's. So if you look at your handout, De Morgan's, it says two things. There's two parts to De Morgan's. Okay, one part is a NOR gate is equal to an AND gate with inverted inputs. Okay, so this is how you would say it in words. An OR gate is equal to an AND gate with inverted inputs. If you wanted to use symbols, well, the NOR symbols like this. So a NOR is equal to an AND symbol with inverters on the input. Okay, so that's half of what De Morgan says. That's half of it, because there's two parts to it. The other part to De Morgan's is that an AND gate is equal to an OR gate with inverted inputs. Okay, so that's how you would say it in words, and then in symbols, you know, here's the NAND gate symbol, and it's equal to the OR gate with inverters on the input. Okay, so there's two parts to the Morgan's. And what we're going to do next, and I think we have enough time to do this. In fact, I think I might finish actually a little earlier than what I thought. But what we're going to do next is we're going to determine the POS for E. And POS stands for, let's write it over here. POS stands for product of sums. Right, SOP is sum of products, POS is product of sums. Now, the next thing I'm going to write on the board, just take my word for it right now, and then in 5 minutes or so, I'll prove it to you, okay? We'll prove it together. And that, since we want to determine POS for E, we start with SOP for not. Okay, so you see, we want to determine the product of sums for E, output E, but to do that, we have to start with the SOP for not E. See, unlike the SOP equation that we can get directly from the truth table, a POS equation, unless you're experienced with this stuff, like you've done this for a while, you can't get from a truth table. And even if you're experienced, you can't get a POS equation from a truth table easily. Okay, SOP is very easy to get from a truth table, right? Because when we wanted E SOP, we just looked up what the ones are. When we wanted not E SOP, we just looked where the zeros, right? But you can't do that for POS. Okay, so the first thing we're going to do, see, we're starting with this SOP equation right here. The first thing we're going to do to get to this POS form is we're gonna knot both sides of the equal sign of this knot ESOP. So I'm gonna knot here, and then I'm gonna knot the other side, the whole thing. Okay. So when you have a double knot over a variable like this, the double knot just cancels out. So this is just gonna be equal. When you have a knot over everything like this, that knot does not cancel out these other knots over single variables of each of the terms, okay? That doesn't work that way. So I'm just gonna rewrite what I have here down here. Okay, so if I make a mistake, let me know if I don't transpose something correctly. Just copying what's up here, I'm not changing anything. Not intentionally trying to change anything. So I think I copied that down right? Those are all. Okay. Okay, so now. Let's go back to. Our NOR gate. Remember we talked about earlier, I erased it, but when we were talking about the NOR gate originally, we wrote that the Boolean. Right, the Boolean expression at the output of the NOR gate is gonna look like this, right? Because inputs get OR together first, and then the whole thing gets knotted. Same type of idea for the NAND gate. Right, the NAND gate, the output, it's gonna be A and B ANDed together, and then the whole thing knotted. Okay. Well, looking right here. Okay, looking at this expression right here at the output where these inputs have been ORed together and then the whole thing knotted. Well, look at this equation. If you consider this to be an input, and you consider this to be an input, and you consider this to be an input, and you consider this to be an input. Well, look, this input is ORed with this, ORed with this, ORed with this, and then the whole thing is not. So can you see that this equation here is a NOR gate? Right? See, this is a NOR gate with inputs. Not C, not G, not S, not C, not G, S, C, G, not S, and C, G, S. See, this equation represents a 4-input NOR gate, right? Where these expressions are inputs. The only difference is, this expression here just has like single inputs, but these inputs are combinations, right? I mean, that's the only difference, but it's still a NOR gate expression. Well, the Morgans tells us that a NOR gate is equivalent to an AND gate with inverted inputs. So I can now write E taking each one of these inputs, inverting them, and then ANDing them together. So you see, I can take this input, invert it, then AND it with, I'm using the dot for AND here. Right? See, I'm ANDing it with this input that I've inverted, and then ANDing it with this input that I've inverted. And then ANDing it with this input that I've inverted. So you see, to go from this to this, I've used this part of the Morgans. A NOR gate's the same as an AND with two inputs inverted. So does everybody see what I did here? Because we're not done. We have to apply to Morgans one more time to get POS, but we're on our way to POS. Okay, but everybody's good up to this point? Okay, well now, just look at each one of these terms. See, just look at one of these terms, like right here. We're taking this input, anding it with this input, anding with this input, and then inverting the whole thing. So if you just look at this, or, look at any one of these terms, what kind of gate is that if you're anding and then inverting the whole thing? That's all that. If you and first and then you invert the whole thing, that's an AND gate, right? That's what we're talking about right here, right? The AND gates, they and the inputs, and then they invert the whole thing. So you see, each one of these is a NAND gate. See, this is a NAND with inputs, not C, not G, not S. And this is a NAND. With inputs not C, not G, S. And this is a NAND, and that's a NAND. They're all NANDs. And De Morgan's tells us a NAND is the same as an OR with inverted inputs. So I can take this term, invert each of the inputs, and OR them together. So you see here, I would get C or G or S. And then this term, I would get C or G or not S. And then here, I would get not C, not G, S. Oh, the boards there, the boards. And then here, I would get not C or not G or not S. Okay, so again, here we apply De Morgan's again, that a NAND equals an OR with inverted inputs. Yeah, so did everybody see what I did here? Okay, well now look. This is POS. Right, because see, it's product of sums. Each of these terms is a sum because it's ORing. And then each of the terms is being ANDed together, which is product. Right, so you see, that's our POS for E. And like I said earlier, we had to start with SOP for not E to get POS for E. So, I just go through this derivation between SOP and POS one time. But then what I expect that you can come up with here, if you take a moment, is coming up with a shortcut to go directly from what we started with, right, the SOP for not E, to the POS for E. Like if you compare these two equations, how could you quickly go between these two? Do you see a pattern? What's the pattern? We had not E, here we have E. Here we had not C, G, not S. Here we have, I pointed at the wrong one, sorry, we're here. So here we have not E, here we have E. Here we have not C, not G, not S. Here we have C, E, S. Here we have not C, not E, S. Here we have C, G, not S. So what's happening here? You can keep going, but it's the same thing, right? Everything's inverted. Right? If you compare this equation to this equation, everything's inverted. All the terms are inverted. What else is you see?
CGS load multiply and then you fill all the others.
Right, exactly that. Here, these are all ANDed. Here, they're all ORed. Also, the terms are ORed, but here, the terms are ANDed. So you see, to go from SOP to POS quickly, you just invert all the terms, right? All the variables, change AND to OR and OR to AND. Okay. So, like I said, I show you the derivation once. But on a test or any assignment that you get, you can just go directly from one to the other by just inverting everything, changing hands to oars and oars to hands. Okay, but this is why. It's applying to Morgan's twice. That's why you can do it. Okay? And again, because this is the most common error. Okay, the most common error I see with this is that you got to remember, if you want POS for E, you got to start with SOP for not E. Likewise, if you wanted POS for not E, you would start with SOP for E. And you know, we went this direction, right? We went from SOP to POS, but you can go POS to SOP. You can go the other direction too. It's the same thing. You're just inverting everything, changing hands to oars and oars to hands. Okay. Now, you may wonder, well, why is it good to know both forms? Well, the reason why it's good to know both forms is because quite typically, one form will give you less terms than another form. Like here, they're equal just because of what the truth table was. But if you have different forms, then you're going to see there's more than just these two. We'll get to two other forms next week. Well, the form that gives you the less terms means the circuitry is less, right? In both these forms do the same thing. They came from the same truth table. The different forms give you the same answer. So if you have one form that requires less circuitry than another form that's going to give you the same answer, use the one that uses less circuitry, right? It's more efficient, more reliable because there's less stuff to go wrong if there's less components. Okay. All right. So let's see what we got left. Actually, I can probably do all these in about 10 or 15 minutes. So do you want me to keep going or you rather take a break? Keep going? Yeah, it's not. This was the most time consuming. The rest of this is going to be time consuming. All right, the next thing is drawing logic circuit diagrams for both SOP and POS. So let's start with SOP. Okay, SOP logic diagram. Okay, well, let's look at an SOP equation like this one right here. Well, an SOP equation, it has terms where we're ANDing, right? We're ANDing the inputs to get these terms. And then the terms are ORed. So what kind of gates do you think are going to be in a logic diagram for an SOP support ANDing and ORed? AND and ORed, exactly. There's another question that could be on that Jeopardy category, right? The answer is right in the question. And in the diagram, these inputs are ANDed. So since we have 4 terms, each term is going to have an AND gate. Right? And see, each term has 3 variables. Each AND gate is going to have 3 inputs. Right? So like here we'll have not C, G, not S. Here we'll have not C, G, S. Let's see, and then C, not G, not S. And then C, not G, S. Right, so, you know, at the output of each AND gate, you're going to have a term, right? So, you know, the not C, not G, S term is going to be at the output of that AND gate. Then the not C, G, S is going to be at the output of this one, right? I could put the other 2, but you getting the idea? Okay, so after these are ANDed together, right, to get these terms, then what do we do to get the equation? What are we going to do? OR them, right? See, OR all the outputs of the ANDs together. So there's just going to be a single OR gate. And the outputs of the ANDs go into the input of the OR. Right? Because the OR is going to take this term and OR it to this one, OR it to that one, OR it to that one. Okay? I mean, I didn't write everything out, but does everybody get the idea? I'm counting on that you could fill this in. right? Because here's where our SOP equation, would be, right? The same one that we have over on the left side of the board. Okay, so does everybody see why these are AND gates and then we have an OR gate? Okay, that's SOP. If you understood where that SOP diagram came from, then you should be able to tell me what the POS diagram would look like. Because look, the POS, the terms are ORed, and then the terms are all ANDed together. So what's the POS logic diagram gonna look like? Yes, it is.
So you just flip the logic here.
Yeah, exactly. It's just the opposite of this, right? Because the POS, the terms are ORed. To get the terms are ORed, and then the terms are all ANDed together. So it's just the opposite. POS is just the opposite of SOP, right? That you're gonna have multiple OR gates, 4 OR gates in this case. And they're gonna be 3 input. And then the outputs of the OR gates go to 1 AND gate. Right. So see, just by looking at a logic diagram, you can tell what form you have, right? Because if you got multiple ANDs and 1 OR, it's SOP. If you have multiple ORs and 1 AND, it's POS.
For the product of sums, you would have the inputs for each one of the OR gates. That would be from the inverted key though, right? Like you take it from the truth table when it's 0, not 1.
Well, remember this equation here, this is SOP, right? It comes from the truth table when the output is 0. But what I'm drawing, that diagram that I'm drawing is this right here.
But those inputs at the bottom, those are the same as the ones that are coming from up there, top, right? Or the inverted form. Not really sure where.
Well, only if you see a bar over it would it be a not. So like when I write, just like I wrote these inputs based on what I had in the equation for the SOP of B, I would write the inputs for this POS diagram based on that equation, that POS equation at the bottom there. So this would be like C, G, S. Is that what the first one is? Then like C, G, not S.
Where you're finding the not S, that's coming from the sum of products for not equal, right?
Not S is just, you have some input S,
Right.
like in a circuit. And, if you want just S, it's gonna go directly to whatever input, you just have that. Well, let me do this. Let me draw it over here. Like say we have our input S, and if an input to an OR gate is just S, then this would go directly like that. But if I want not S, I'm just gonna put it through an inverter before I go to where the not S is.
Oh yeah, I'm just asking like where you're getting the how you're looking at it, because the inputs for that, there's a certain way you have the inputs of it. Each one of them has C, G, and S, but where you're finding where to put the nots over them, that's coming from that stuff up there, right? Because we got that from the truth table. I guess I'm just wondering how we went from the truth table, and then we got the sum of products, and then we're plugging that into the logic right there. I'm not. Maybe I'll probably rephrase the question.
Well, let me try to answer your question in multiple, because I think it's like a multiple part question. I mean, the first thing is, and I think you said this, that this equation is coming directly from the truth table. This is coming from where we see the one. This SOP for not E is coming from the truth table also. Just the 0, okay? The POS equation, again, unless somebody's like really experienced and really what's happening when they're able to go from a truth table directly to POS is they're doing the Morgan from their head, basically. So, at the very least, I can say that it's more difficult to go directly from a truth table to POS. It's easy to go from the truth table to SOP. Okay, but what I'm showing with the diagrams is that when you have any sort of SOP equation, it's going to be terms that are ANDed together and then all OR. So no matter what kind of SOP you have, whether it's for E or not E, it's gonna be AND gates with a single OR. And then if you have any sort of POS, because you have, you know, ORs and then everything's ANDed, that's why it's the flip. Okay,
Yeah,
is that,
yeah, I'm
Better?
saying what's right from, I was just right.
okay. Okay, any other questions? All right, what's left here? That was the logic circuit diagram. Okay, let's go to a timing diagram. This timing diagrams are important because in the lab, when you go to check that your lab design is working the way it should and it's 100% working, you do that by looking at a timing diagram in the simulation of Vivado. And a timing diagram is really just a truth table shown over a period of time. So for example, in this timing diagram here, let's see, this would be our S input, our salsa. This would be our egg input, and then this would be our chip input. So, you know, this is just showing the values of each of these inputs as time progresses. You know, like over here at on the far left side of the timing diagram, that's when, you know, time equals 0, that's your t equal to 0, right? And as time progresses, we're showing how the inputs are changing in time. So if I just look at, you know, say the time right here, well, at this time, all my inputs are 0. So if my design in Vivado is working the way it should, like let's say you were actually doing this truth table in Vivado, you won't be, but let's say you were. Well, you would expect, based on the truth table, that when all these inputs are 0, the E output is 0. And you would also expect that during this time where S is 1, but C and G are both 0, well, that your output E would also be 0. Right, because that's what the truth table indicates. And then when we have 0, 1, 0, which would be this time here, let's say, right, where S and C are both 0, but G is 1, well, we would expect our output E to be 1. Now, G changes right here to a 1. So that's when we would expect our E output to change to a 1. Okay? So, do you want me to keep going or you get the idea? I mean, we could keep going for the whole truth table. It's the same idea. You're just looking at in time what your inputs are equal to and making sure it corresponds with the output that you expect. And you get the expected output from your truth table. Okay? You know, if you've watched my video, I'm pretty sure in the video, the intro to Vivado video, I show that, right? I show like the timing diagram and that it's giving us the intended truth table. And that's what you have to do in lab 0. Okay. All right, let's see, just 2 more things. Black box diagram. The black box diagram just shows you what your main inputs and your main outputs to your system or design is. So, like for example, for this thing, for what we've just done with the chips, eggs, and salsa, you know, maybe we call it breakfast, dairy breakfast, maybe. You know, your black box diagram should always have a name. And then on the left side, you show the inputs. So here we just got 3 inputs, C, G, S. And on the right side, you show the outputs. Here it's just 1 output, E. I mean, sometimes inputs are shown on the bottom or the top. We'll get to that later, but most, you know, in the basic sense, the inputs are on the left side, the outputs are on the right side. Now, one thing that's going to come up later in the quarter, okay, just a little preview, is that you'll have designs eventually that have more than 1 bit. Like you can have multiple bit inputs. You can also have multiple bit outputs. And when an input or an output is more than 1 bit, we indicate that with a slash and then a number indicating how many bits. So like if you saw something like this, that would mean that this input C had 4 bits, not just a single bit. If it's a single bit, we don't put a slash. Like it would be incorrect to put a /1. It's understood that if there is no slash, it's a single bit. Right, and same thing, like your output could be multiple bit, like you might have eventually, well, later on in the quarter, you will see an output that has 8 bits.
Does that mean like 8 bits in parallel?
Yes,
Okay.
yeah, exactly. Yeah, you'll see, when we get to, driving displays that are on the basis board, on your basis board, you got 4 7-segment displays. Well, those require multiple bit, data, not just a single bit. Yeah, we'll get to that. All right, last thing, and that's in system Verilog, how you would represent a SOP or POS. I'll just do an SOP, and I think I show this in my intro to Nevada video too. So let's say you wanted to write this SOP equation in system Verilog. Well, the first thing you would do is type assign. And then you would put the output, which here is E. And then the equal sign. And then for these terms, although it might not be required to do, I like to do it. I like to put each term within parentheses. So like that first term there, I put parentheses. And now in system Verilog and also Verilog, you can't do like a bar over a variable. So in Verilog, in system Verilog, when I say Verilog, I mean system Verilog. Okay, in system Verilog, the not is a tilde, right? So to get not C, you put tilde and then the variable. That would be not C. Now, this tilde is for what's called bitwise, which is what we're doing right now. Later on in the quarter, we're going to be doing what's called behavioral modeling in Verilog. So later, this isn't for several more weeks, you'll see that not is also an exclamation point. Okay, but for lab 0 up until a few more weeks, if you want to not something, use the tilde. Okay, this is later. Okay, it won't work. If you try to put an exclamation point in front of the C, it's not going to work. Okay. Then we have to and it. Now, in Verilog, you can't just put 2 variables with nothing in between. Like it's not going to take it as and if there's no symbol in between. So in Verilog, and anytime you want to and things together, it's the ampersand. It's the symbol that's above 7 on your keyboard, the ampersand. So you'd have to go ampersand, and then like G, and ampersand, tilde S. That would be that. Yeah, I would put each term in parentheses. And then or. Okay, or in Verilog, it's not the plus sign because plus in Verilog means add. So the or is a straight line or straight vertical line. Okay, so you'd have to put a straight vertical line, and then like you could have your next term in parentheses, and another vertical line, the next term, vertical line, next term, and then you end it with a semicolon. Okay, so that's how you would do an SOP in Verilog. And then if you need to do a POS, it's the same idea. It's just, your terms are going to have or, so they'll have the vertical line, and then you're going to have that ampersand between the terms. But it's the same idea. Okay. All right, so let's see. On Canvas, just 2 more things I want to show you quickly. Okay, the activity is on Canvas under Meeting2. On here. Okay, so there's two parts to the activity. The first part is just to take this SOP equation for F and write the truth table for it. So, you know, I went from truth table to equation in class. I just want you to go the other way. I give you the equation, now show me what truth table it came from. And then the circuit diagram and also the Verilog code, and then write it as POS. And again, when you write it as POS, you don't have to show me the derivation. You can just, you know, do like we said before. You just got to invert everything, change ands to ors and ors to ands. Now, I couldn't do a bar over the not variable, so I used a little tick mark. So like here, this is U, not V, W. Yeah, it's hard to see the tick mark on the screen, but if you look on Canvas, the actual document is clear. And then the second one, well, you can see there isn't a diagram here, but the diagram for number 2 is up on the board. People over there can't see it, but it's right here. Okay, so for number 2, you're gonna have to come up, take a picture of this diagram, and then I posted the solution over here on the wall, so you can compare your answers to mine. Okay, so that's the activity. So any question on anything about the activity? There's one more thing I want to show you, but no questions about this. And you know, just like last week, everybody do their own work, and then each table pass in one submission. But the last thing I want to show you before you start working is, and I pointed to this last time, I think, but I don't think we actually looked at it. And that's, see this document here, lab demo criteria. Make sure to take a look at that before you make your video for lab 0. Here. I mean, we did talk about, you know, what gets graded, what you do, and what you turn in. But read through this because it talks about how to make your video clear. Okay, you know, having good lighting, because the grader has to be able to see the position of your switches, right? Because the key thing to show that your design works 100% as it should is you got to demonstrate that it does the truth table. And the grader has to see that you're actually doing the right inputs with the switches, okay? Because your inputs are going to be position of the switches on your basis board. And the output is going to be shown with an LED. So, you know, the LED has to be visible so the grader can see whether it's on or off. Okay, it should be on when it's an output of 1, should be off when it's an output of 0. Okay, and also like labeling things, like labeling your inputs, especially when we get to more complicated designs, it is very important to do. Okay, because as I mentioned last class, your design has to be 100% working to get those 3.5 points. So you want to make sure that your video is clear and that it can be seen that it's working the way it should. This is where having a lab partner is valuable, right? Like I strongly recommend that you just don't have one person make the video. Have both people there because then you can check each other. You know, oh, did we cover all this? Because what has happened in the past is, you know, somebody will have a truth table of 8 cases and they only do 7. And that's not 100%, right? If you don't do one of them, we don't know. The grader doesn't know whether it's working for all cases. Okay? And again, you only get one shot to get graded. So make sure what you turn in is good before you turn it in. Right? So it means like double checking, being meticulous, make sure stuff is right before you turn it in. Okay? All right, last thing before I shut up and let you go to work is just remember, if you know who you want to work with, write the names up there, because I'm going to start assigning people in about 5 minutes or so. So if you know who you want to work with and it's not already up there, please put it up there now, okay? So any questions before you start working on the activity? And then right after the activity, work on the lab. Again, once you get to the lab, you don't have to stay here if you don't want to. If you want to work on the lab somewhere else, that's fine. But you have to stay here until your table is done with the activity. Okay? All right. You can get to work. Ethan will be here in about 30 minutes. So yeah, ISA.
Lab 0 have like
Yeah. Well, you'll see in my video, because I think I showed the constraint file in video.
Yeah.
That, you're gonna use switches to the input connected to the input. And there's only one output, and you just need one to the.
Oh, okay. I watched the video, I don't have the one yet, maybe, but the constraints file, like the common thing and stuff, I didn't understand like that. I don't know, like the formatting for that file or something.
Were you able to find the constraints file?
Yeah, I have that.
Yeah, it's just, when you look at the constraints file, if it's got a number, I think 2 number signs way to the left, that means it's comment. So to uncomment, you have to get rid of.
Yeah.
Yeah.
I just don't like, I don't like. Yeah, I think that probably works better for use the diagrams and whatever.
Okay.
I would use not worry here and like how you got these, but they're just matched to like for this one, which is the some equipment. You got that from is right here, it's a PA or your example or so yeah.
Oh, I agree.
Yeah, I couldn't see a little bit. The input for the song products would be that, but when we did the product with some, you just got them with these. That's what I was noticing.
Yeah, but you see. The end result of what was after the product comes this thing on, this is weird diagrams.
Yeah, but these are here, that comes there, and then this.
Well, no, it was actually this goes with this tree because each one of these is getting converted as it works together. It's on 2 inputs that go to the well, yeah, it's just that
Oh,
it's taking the first row, this can bring the last row. But no, it's like this. Again, you go quickly, everything gets inverted. And so it's order.
That's what I was thinking about like here, but actually the input is still this, it's just inverted for each one. Well, each.
Okay, well, when, remember, to get POS, you have to start with.
Oh. Okay, that's what those. So if I was on like, do you want to just like, you're like, one is you take and so for not you for each individual, that's what, and you put it here, if that's the inputs for the key ones. Okay, there you go. That's
All right, yeah, sorry.
but that was like, it was just.
Yeah, no problem.